Today's speaker is Dr. Brenna Flaugher. She grew up in Princeton, New Jersey, where her parents still live, and she went to Bates College in Lewiston, Maine, majored in physics. She went in there thinking she was going to be pre-med, but just like me, chemistry is just a little bit too hard, so she went to physics, which is much easier. So she got her PhD later from Rutgers, which is the State University of New Jersey, and then she came to Fermilab as a graduate student, much like me. And while she was still at Rutgers, and then she got a job here, much like me, in the mid-1980s. You know, had parallel careers at some level. And she worked at CDF for 18 years as one of the primary scientists there, working on the different things from online computing hardware, coordinating, rigging of the multi-ton detector, building the silicon vertex detector, etc., etc. Then in 2004, she became the project manager for the Dark Energy Survey, which is, of course, the heart of her presentation today. Her main task there was to build a 570 megapixel camera to take pictures at the end of that telescope. Of course, as you know, a regular camera like mine, which is actually pretty good, is 18 megapixels, so I want her camera. So without further ado, Dr. Flaugher.
Yeah, my camera's bigger. A little less transportable, though. Okay, so I'm going to talk about the cosmic frontier, which is going to turn into a talk about the Dark Energy Survey and not much the other things at Fermilab, but that's the way it is because I'm giving the talk. So, as Elliot said, I started at Fermilab in the 80s on one of the particle collider experiments, CDF. And my particular area of study was on the smallest things in matter called quarks. We're smashing the protons and antiprotons together to find out how the quarks interacted, what happens when you smash them together. And so then, after 18 years or so of that, this new project came along called the Dark Energy Survey. And what I find is fascinating is now I'm studying really the largest things in the world. These are clusters of galaxies. A cluster of galaxies is an actual object, and there really isn't anything bigger than a cluster of galaxies. And so, you know, here at Fermilab, we're spanning both the tiniest things in the universe as well as the largest things. So I'm going to talk about dark matter and dark energy. What are they? Why do we think they exist? How do we look for them at Fermilab? And why do we care? So feel free to ask questions anytime. So what is dark matter? So it's called dark matter because we can't see it. It's some sort of invisible matter. We call it dark because we can't see it, and matter because it feels gravity. Because gravity acts on mass. And this dark matter behaves as if there's some mass there, but we can't see it. So it's really that simple. It's dark, we can't see it, and it feels gravity. But it's not normal matter. Normal matter, like atoms, the stuff that we are familiar with, interacts with light by emitting or absorbing light, and this dark matter doesn't. There's no signal for it. So it must be something new, and there are many theories for what it could be. Some are more realistic than others, but as yet, there's no dark matter particle that's been discovered. So why do we think it's there? Well, there's two main pieces of evidence. One, galaxies rotate too fast. The stars on the edges of galaxies are going much faster than they would if all the mass were just in the stars that we can see. And the one way to do that, to get that to happen, is to have a lot of mass that you can't see. The other thing is that galaxy clusters, which are, we believe, large clumps of dark matter with galaxies in them, they act as large lenses. And you can actually see that this clump of dark matter distorts the images of the stars and galaxies that are behind that clump of dark matter. So I'll show you some examples of both of these. So this is a galaxy that's a lot like the Milky Way galaxy. Our sun would be out here on the edges somewhere. And this thing is rotating. And the stuff out here, it turns out, is rotating about as fast as the stuff inside, where there's a lot more mass, and thus that you can see. Out here, you can't see very much mass. There's very faint stars, but there's not very much of them. So the speed at which something out at a large radius is moving tells you about how much mass is inside of it. I'll give you a few little equations. You may have seen this before. The velocity, here you have the velocity